Hey everyone, welcome to CS61B's Midterm 1 Spring 2025 question 2 walkthrough video. My name is Phoenix, and yeah, let's just get straight into it. So the problem says that given a row of a 2048 board, we can define the row-wise drop count of a row as the number of elements in the row which are strictly less than the value immediately before them. So as an example, we can look at this row. We'll start at 128. There's something before 128, so we'll skip it. Then we'll go to 64. Well, 64 is strictly less than 128, so add a tally. We'll go to 32. 32 is strictly less than 64, so I'll add a tally. And then 16. 16 is strictly less than 32, so I'll add another tally for a total of 3, which is exactly what we get here. The problem also defines a notion of a column-wise drop count, which is the exact same thing, but for the columns. So for example, we could look at this column of the board here. We'll start at 128. There's nothing before 128 in this column, so we'll skip it. Then we'll go to 64. 64 is strictly less than 128, so I'll add a tally. 32. 32 is strictly less than 64, we'll add a tally. Then 16. 16 is strictly less than 32, so we'll add a tally for a total of 3, which is exactly what we get here. Lastly, we also define the total drop count, which is the sum of all of the row-wise drop counts and column-wise drop counts for each row and column in the board. And so what we're doing here is we're saying for each row, we compute the row-wise drop count. We'll get some values here. Then for each column, we compute the column-wise drop count. In this case, we'll get 3, 3, 3, 3, 3, 3, 3, 3. And then we'll add up all these guys together, and that'll get us our correct answer, 24. Cool, I think we're ready for the next problem. Or I guess for the first problem. All right, cool. So this problem actually asks us to implement an algorithm which computes this total drop count that we defined earlier. And so maybe your gut instinct to approaching this problem is to say, well, maybe we'll go row by row, and we'll compute the row-wise drop count for each row. Then we'll go column by column, and we'll compute the column-wise drop count for each column. We'll take all those guys, sum them together. That gets us the right answer. And this is a perfectly fine approach, except for the fact that it's a little slow. And the reason why it's slow is maybe we'll consider the position 32 in our board. And when we compute our row-wise drop counts, where we're going row by row ad nauseum, we're going to visit 32 once. And when we visit each column and compute our column-wise drop counts, we'll visit 32 again. And so we're doing the same work essentially twice. We're visiting 32 twice, we're visiting every entry twice. And the key observation here is whenever we visit an entry like 32, I'll change my color here. What I'm really doing is I'm comparing that entry to the entry to the left of it when I do my row-wise drop counts. And then I'm comparing that entry to the entry above it when I'm doing my column-wise drop counts. And so take a few seconds and think about how I can combine these two steps into a single step so that I'm not visiting each entry more than once. Okay, welcome back. So you might be thinking, well, why not just do them at the same time, right? So maybe I'll go through each entry in my board and I'll say, well, what's the thing to the left of me? And then what's the thing above me, right? So if I have a position ij, and which is just a position in our board, I'll say, well, if the thing to the left of me, our board is called board, if the thing to the left of me, that's going to be this index here, if that's ever greater than me, where I am ij, then I'm going to add 1, right? Because that's a row-wise drop count. Similarly, if the thing above me, board of ij, or I guess I minus 1j in this case, that's the guy above me, same column, if that's ever greater than me, apologize for the poor handwriting here. If that's ever greater than me, I'll add a +1 because that corresponds to a column-wise drop count. And so if we do this procedure for each entry ij in our board, we're going to compute the right answer, right? Because all we're doing is we're just combining those two steps together. Now, one thing to note is that we have to be a little bit careful here. If we look at maybe something in the first column, there's nothing to the left of these elements. So if we try to do, let's say, we're looking at this entry 64, we tried saying, well, what's board of 0 minus, or board of 1, 0, -1, what's to the left of it? We're gonna get an out of bounds exception. And if I do the same thing for 32 and I say, well, what's above 32? Well, there's nothing there. I'm gonna get another out of bounds exception. So that's the second key observation we have to make. The first is that we can combine our steps and go entry by entry in our board. The second is that we have to be wary about these cases where there's nothing above us or there's nothing to the left of us. So let's see how the skeleton code kind of mirrors our intuition. Okay, cool. So we've lucked out. We see a nested for loop. Whenever I see a nested for loop in a problem that has a two-dimensional array, I'm thinking I'm gonna have to go through elements of this array. So we already know what these two indices could mean. Maybe I'll let I correspond to the rows in my board. So maybe the I's control my rows, and then maybe the J's control my columns. And I already know what I have to do. Well, I'll just say if the guy to the left of me, if that's greater than me, I'm gonna add one. And then same thing here. If the guy that is above me is greater than me, I'm also gonna have to add one. But here's where we have to be a bit cautious. So maybe we'll focus on this first condition here and we'll say, well, I want to safeguard against checks in this first column here, right? I never want to check to the left of any element in this first column because that's going to cause me problems. Well, one way we can get around that is just by saying, well, I'm just going to start in this column here. Right. So if I start in this column here, then I'm just going to be comparing, these columns, basically everything from the first column to the last column. That's perfectly fine because we do for each column, for each entry in these columns, each entry has a left element. So there's no out of bounds exceptions here. This is a perfectly fine way to go about it. So say J goes from the first column to the last column, which is just board dot length. And I'll make a small remark here. And that board dot length is the same thing as board of 0 dot length or board of 1 dot length. And that's just because our board is a square, or our board is square. So those dimensions are the same. Okay, now the last thing we have to do is safeguard against these upward checks, right? And so your natural inclination would be to say, well, why don't we just do the same thing, right? We just cut off this column, and then we just consider all, or sorry, cut off this row, and then we just consider all rows below that first row. And we can't actually do that, and the reason we can't do that is because we're hard-coded to start at that first row. So you might be thinking, well, what's the best solution here? And if you've seen the solution, it may seem a little unintuitive, but I'll try to break it down here for you. And so the idea is, well, let's say we get to a entry 64. What if we were instead to look at its mirror image 8 and compare 8 to its upwards neighbor? And then if we get a valid column-wise drop count from that, we'll just add 1, right? And we can do the same thing for another element, and maybe we'll hit 64 and we'll say, well, I'm going to look at its mirror image, which is also 64, and I'll compare it to its upward neighbor, and if that's a valid drop count, I'll add 1. And the reason why this works is because maybe if I'm going back to 64 and I compare it to its mirror image 8, and then I make that comparison, well, when I get all the way back down to 8, when I get back to this 8, I'm going to do the exact same thing. I'm going to look at 8's mirror image, which is 64, and compare 64 to its upwards neighbor, and so I'll make that comparison still. And so if we were to say this formally, we'll say, suppose we get to a point ij initially, and we want to compare ij to the position I minus 1j. Well, it suffices to check j minus 1i, which is sorry, suffices to check ji, which is the mirror image, and compare it with its upward neighbor, j minus 1i. Because at some point, we're going to hit that position ji, and once we do, that's when we'll be making that comparison. So there's kind of this nice argument by symmetry going on. And you might be saying, well, how does this guarantee that we're going to be hitting things on the border, right? If we're not even starting in this column. And that's kind of where this mirror image idea comes in, because we'll be hitting this first column. We'll be making upward comparisons in this first column, as long as we're hitting these entries in the top row, right? So 2 will hit the 8, 0 will hit the 2. And so we're guaranteed to be making those upward comparisons. So we'll have to amend what we have here a little bit. And we'll say, instead of comparing myself to my upward neighbor, I know I'll run into problems when I do that. So I'm going to instead compare my mirror image to its upward neighbor. And I'll hope that this good deed pays off, because once I hit my mirror image in this for loop, that's going to make me compare myself to my upward neighbor. Okay, and then we're just free to go from the first row to the very last row. And this completes the problem. So this problem is asking us to implement the find max method, which finds the largest tile in the board. So if we just go through the skeleton code, we can try to see how it matches our intuition. So maybe if we have a board which looks like 2, 3, 4, one way to find the maximum is just to go through each entry and see if it's the largest than what we've already seen. And so this is kind of matching that, right? So for each row, we'll go through each row, and we'll check all the tiles in the row. So 1, 2, and we'll say if that tile is ever greater than the maximum tile that we've seen, or the tile with the maximum value that we've seen, that's going to be our new max tile. So we'll just say, well, if that tile is ever greater than the maximum tile we've already seen, then the max tile that we've already seen isn't the max tile. So we'll set it to that tile. Now we need to figure out what these types are. In Java, we store a two-dimensional array as an array of arrays. So we can think of the Java representation of this board as looking something like 1, 2, comma 3, and 4. And so for each row in this board, that's going to be another just one-dimensional integer array. So this is going to be int bracket. And then for each element inside of this array, well, that's just an integer, right? That's just this right here. So we'll put that right there. And to put it all together, we're iterating through each row, which is a array. Then we're iterating through each element of that array, and we're seeing if that element is greater than the maximum tile we've already seen. If it is, that maximum tile, or the maximum tile we've already seen, isn't the max tile, so we set it to be the tile we just saw. Okay, now let's move on to the next problem. For this problem, we're asked to implement a board comparator class, which compares boards by their largest tile value. And if they're equal, then we compare their total drop counts and use it as a tiebreaker. So first things first, we need to figure out how to actually define a comparator class. And so we know that any comparator class implements the comparator interface. And if we remember, the comparator interface looks something like this, right? Comparator, I'm omitting some syntax here, but it's parameterized by type T and has a bunch of methods, and one of the methods that you must implement. Sorry, that's compare which takes one object of a type T, another object of a type T, and then it spits out some metric of distance between the two types. That could be something like some kind of measure of O1 minus some kind of measure of O2. What's important here is that we have to specify a type, and that type must be the same type as the things that we're comparing. So let me just get rid of all of this. Erase. So I already know that this is going to be, if we look at what the type of these objects are, these are two-dimensional integer arrays, so we're going to parameterize this with two-dimensional integer arrays. One thing you might be concerned about is, hey, isn't this supposed to be a reference type? I see an int, and an int is a primitive type. And you're right to be concerned, but the key observation here is that an array is a reference type. And so a two-dimensional array is a reference type, regardless of what type of elements that array holds. So this is perfectly valid, and you won't get any kind of compiler error. Cool, now that we have that, I probably should have, oh Lord. Hold on, I'm gonna fix this. We're back. Cool, so now that we've actually defined what this implements, we can start with approaching this problem. So it says that we want to compare boards initially by their largest tile value. Well, we know how to find the largest tile value in a board. We just did that. That'll be for tile A, find max of board A. Similarly, the largest element in board B is just find max of board B. And then it says if these are equal, so if these two things are equal, so tile A is equal to tile B, luckily we have a second condition, which instead just uses their total drop counts to compare them. And so we know how to find the total drop counts. It's by using this total drop count method. So that's going to be total drop count of board A. It'll be the same thing with board B. And then remember, any compare method returns any compare method of concerning board A and board B returns some metric of board A, or I guess measure of board A, minus some measure of board B. So we're going to return their difference in that exact order. So it'll be score A minus score B. And remember, if these two weren't equal, then we'll use that as a deciding factor for their comparison. So that'll exactly be tile A minus tile B, completing the problem. All right, guys, smash that like button, subscribe.